Hello guys, welcome back to another video. Today we're going to see where this formula comes from. We're going to prove Euler's formula. But first of all, let's take a look at it. There is an exponential here, a cosine and a sine function. And what does an exponential has to do with cosine and sine? And why is the imaginary unit I, that is the square root of -1? It might seem confusing, but don't worry, we are going to prove it. But to do it, we need Maclaurin series. Basically, if we have a function f of x, we can write this function as an infinite series. This is the series, the sum from n equals 0 to infinity of the nth derivative at x equals 0 of this function divided by n factorial times x to the n. Wait, this is weird, right? What does this function has to do with this series? Well, this is going to be a topic for another day, and this Maclaurin series and also Taylor series are so important in maths. And basically, a Maclaurin series is a series that represents our function as an infinite series, and this works for every function f of x. So we are going to find the Maclaurin series of e to the x, cosine of x and sine of x. Okay, to find the Maclaurin series of e to the x, our exponential function, so the case where f of x equals e to the x, we first have to find the derivatives of e to the x at x equals 0, because in this formula we have the nth derivative of our function at x equals 0. And well, this notation might seem weird, but f of 0, so I don't know how to say it, the zeroth derivative of our function at x equals 0. Well, this is just our function at x equals 0. This is just a notation to say simply the function. It is not a derivative of the function. So let's start. Differentiate e to the x. F prime of x is e to the x. The derivative respect to x of e to the x is just e to the x. Let's differentiate another time and we still get e to the x, and we can go forever. And in general, the nth derivative of our function, that is e to the x, is always e to the x. So it's very simple to work with the exponential function when there are derivatives, because if we try to differentiate it, we just get e to the x. Now let's evaluate this at x equals 0. So f of 0 is just e to the 0, that is 1. And the same thing for the first derivative. F prime of 0 is just e to the 0, that is 1. So the second derivative of our function at x equals 0 equals e to the 0, that is 1. And in general, for the nth derivative of e to the x at x equals 0, we get 1. So we know that our exponential function e to the x can be represented as the sum from n equals 0 to infinity of the nth derivative at x equals 0 of our function, that is 1 over n factorial times x to the n. And now let's expand this series just to make things more comfortable. This is for n equals 0, 1 over 0 factorial times x to the 0 plus 1 over 1 factorial times x to the first power plus 1 over 2 factorial x squared, and so on. Don't forget that those are infinite terms because this is an infinite series. And we can simplify a bunch of things, because 0 factorial is by definition 1, so 1 over 1 times x to the 0 is just 1, so 1 plus 1 over 1 factorial is 1 over 1 times x to the first power, so this is just x, plus x squared over 2 factorial, and we can add a bunch of terms just to figure out how this series behaves. So this is x cubed over 3 factorial plus x to the first power over 4 factorial, and so on. Now we have a Maclaurin series for our e to the x function. Now let's do the same thing for cosine and sine. Okay guys, so let's do it for the sine function. F of x equals sine of x. We have to find the nth derivative of sine of x at x equals 0, and so let's try to differentiate sine of x. F prime of x equals the derivative of sine of x, that is cosine of x. Then the second derivative of sine of x is the derivative of cosine of x respect to x, that is minus sine of x. Then the third derivative of x equals the derivative of minus sine of x, that is minus cosine of x. And if we differentiate cosine of x, guess what? We get back to sine of x. So basically we continue to differentiate, and this path repeats itself. So we always have sine of x, cosine of x, minus sine of x, minus cosine of x, sine of x, cosine of x, and so on. This is a very interesting and useful pattern, because now we have to find these derivatives but at x equals 0. So let's just plug 0 in this, and f of 0 is sine of 0, that is 0. Then cosine of 0 is just, so f prime of 0 is cosine of 0, and cosine of 0 is 1. Then we have the second derivative, that is minus sine of x, and we know that this function at x equals 0 equals minus the sine of 0 is just 0, so this is 0. And we know that the third derivative at x equals 0 is minus cosine of 0, so cosine of 0 is 1, so minus 1. So we have 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. So we can try to write down our series. We have sine of x equals 2. The nth derivative of our function at x equals 0. So f of 0, that is 0 divided by 0 factorial times 0 to the 0 power, plus 1 over 1 factorial x to the first power, plus 0 over 2 factorial x to the second power, minus, because we have this minus sign here, 1 over 3 factorial x to the third power, and so on. So we can rewrite these as, this first term is just 0, so 0 plus 1 over 1 factorial x to the first power is just x, and 0 divided by 2 factorial times x squared is just 0, minus 1 over 3 factorial times x cubed, and we can rewrite this as x cubed over 3 factorial, and so on. And this series behaves like this if we write more terms, and it is x minus x cubed over 3 factorial plus x to the fifth power over 5 factorial minus x to the 7th power over 7 factorial plus x to the 9th power over 9 factorial plus dot dot dot. You can clearly see this pattern if you write more terms than we did. It is not that difficult. You have just to take into account more terms, and you see that this pattern goes forever, because we always have 0, 1, 0, minus 1 as the nth derivative of sine of x at x equals 0. Okay guys, now we have to do the same thing for cosine of x, so we need the nth derivative of cosine of x at x equals 0. Remember that sine of x, if we differentiate this function, we get cosine of x. If we differentiate cosine of x, we get minus sine of x. If we differentiate minus sine of x, we get minus cosine of x, and if we differentiate this, we get back to sine of x. And at x equals 0, sine of x was 0. At x equals 0, cosine of x is 1. This minus sine of x is just 0 at x equals 0, and minus cosine of 0 is minus 1. This is our previous pattern, but now we start at cosine of x. So we start from here, we take the derivative and we get here, we take the derivative and we get here, derivative and we get here, and so on. So we don't have to do everything again, we just have to start from cosine of x. So let's write our series. So if we have cosine of x, it can be written as cosine of 0, that is 1 over 0 factorial times x to the 0 power plus 0 over 1 factorial x to the first power minus 1 over 2 factorial x to the second power, and so on. And this can be written as 0 factorial is just 1, so this is 1 plus 0 divided by 1 factorial times x to the first power is just 0, so we have plus 0 minus x squared over 2 factorial, and if we continue to do that, we get plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial plus x to the 8th power over 8 factorial, and so on. Now you can see the pattern. Okay guys, now we have our three series right here for e to the x, sine of x and cosine of x. But why do we need those series? Well, there is a simple explanation to this. Notice that in this formula we have e to the I theta. So why don't we take the exponential function and instead of x we write I theta? It works because the exponential function isn't just defined for real numbers. It is also called complex exponential function, so we can do it. We can take as inputs complex numbers. So let's try to do this. We have e to the I theta equals 1 plus x, so I theta, plus x squared divided by 2 factorial, so I theta all squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the first power over 4 factorial. And this goes on forever. Now you might say, why do I need to write all of these terms? Well, because it's better to understand the path and not just guess how it is going to behave. Like this, we can see more terms and we're able to predict the other terms without taking all the infinite terms into account. So it's always better to write more than just one term. Now, what can we do with this equation? Well, I is the square root of -1. So I squared, by definition, equals -1. Then I cubed, well, this is equal to I squared plus 1. So this is I squared times I. And I squared is just -1, so this is minus I. But then what is I to the 4th power? Well, this is I squared plus 2. This is just I to the 2 plus 2 power. So this equals to I squared times I squared, and this is minus 1 times minus 1, and this is plus 1. And we see another pattern that is minus 1, minus I, 1, and we can also check I to the 5th power. This equals to I. This is equal to I to the 4th power plus 1. That is I to the 4th power. So 1 times I to the 1st power. That is I. So this equals I. And now you can see this pattern: minus 1, minus I, 1, I. And just out of curiosity, I to the 6th power is I to the 5th power times I, and I to the 5th power is I, so it's I times I, so I squared. This equals minus 1. So we can see this pattern minus 1, minus I, 1, I, and so on. So we can rearrange our series like this. This equals to 1 plus I theta plus I squared is just minus 1, so minus theta over 2 factorial plus I cubed is just minus I, so minus I times theta over 3 factorial and theta cubed, don't forget that. Then we have I to the 4th power, that is 1, so plus theta to the 4th power over 4 factorial and so on. Now let's add some other terms just to be sure about it. We have I theta to the 5th power, that is I times theta to the 5th power over 5 factorial. Then we have to the 6th power, so this is minus theta to the 6th power over 6 factorial and so on. Now we can rearrange again this expression and just put all the terms with I together and all the terms without the imaginary unit together. We have 1 minus theta over 2 factorial plus theta to the 4th power over 4 factorial minus theta to the 6th power over 6 factorial. And then we have all the terms with the I, and we can even put I in front of them just because it's a common factor to all of the terms. So this is just theta minus theta cubed over 3 factorial plus theta to the 5th power over 5 factorial and so on. Sorry, I forgot to put plus ... just to say that this is an infinite series and this is another infinite series. Now those two look familiar to you because this is the Maclaurin expansion of cosine of theta, while this is the Taylor expansion of sine of theta. In other words, e to the I theta equals cosine of theta plus I, because we mustn't forget the I, times sine of theta. And here it is our formula. And there is a special case, but we're going to cover it in another video. That is e to the I times pi equals cosine of pi minus I sine of pi. And from trigonometry we know that cosine of pi is just minus 1, sine of pi is just 0. In other words, e to the I pi minus 1 equals 0, and this is called Euler's identity. How cool is that? I mean, what a nice formula. If you enjoyed this video, leave a thumbs up, share it with your friends. Don't forget to subscribe to my channel, leave a thumbs up, and until next time, bye.